Okay, lesson 45, Introduction to Coordinate Proofs. So there is a hint if you are not given all the coordinates and you're just asked to use a coordinate plane to prove something or other. A lot of times if you can put one of the vertices at the origin, that will help, like with distances and stuff like that. So if you're not told otherwise, basically if possible, place a vertex at the origin. So I'm going to give an example where you would have to do that, or where you could use that hint. A rectangle DEFG has a length of 5 units and width 3 units. Position it on the coordinate plane. Now this is not a proof, but it's just, put it on a coordinate plane. And it's just a lot easier if you just put it, one of the vertices at 0, 0. The length is 5, so we go over to 5 on the x-axis. The width is 3, so we go up to 3. Put a coordinate there, and then at the point 5, 3 would be your point. And there's the 4 coordinates drawn on the coordinate plane. Now we're going to do one that is to prove that a triangle is isosceles. I gave you kind of that example at the beginning of class. So we're going to use a coordinate proof to show triangle LMN is isosceles. So we're going to put it on the coordinate plane. 0, 0 will be my L. 2, 4 is N. And M will be 4, 0. Andrew?
Will they ever ask us, if, to reflect it over an axis?
To reflect over an axis? Yeah, probably.
To prove that it can be? To prove.
Oh, like if it's symmetrical about an axis
Yeah.
of symmetry? Yeah, you might. I can't remember though all the problems, but that could be one. So if we're proving this is isosceles, basically we're going to use the distance formula to show that two sides are equal to each other. An isosceles triangle by definition has 2 or more, at least 2 sides congruent. So really you only have to show 2. You don't have to show that the third is different or anything. You just have to show 2. I'm assuming it's these 2. So I want to do the distance formula, which is your difference in the y's squared plus the difference in the x's squared. All of that square root. So that's sum, square root of that sum. So the distance of LN equals, and basically you just show your work. So we have 4 minus 0 squared plus 2 minus 0 squared equals square root of 16 plus 4, square root of 20, which is 2 root 5. So the distance between L and N is 2 root 5. And then we can just do the distance between M and N. So it's 4 minus 0 quantity squared plus 2 minus 4 quantity squared which equals square root of 16 plus 4, square root of 20, 2 root 5. So because, so then we finish with the sentence. This is a proof. So you say because segment LN is congruent to segment MN, the triangle is isosceles. And there you go. So this is what the proof would look like. It's basically showing your work and writing a sentence like a conclusion type sentence. Samuel?
Just a little bit so
Oops, it's in like that. Sometimes you're asked to draw a picture on a coordinate plane and they don't give you the vertices, they give you a variable. So for instance, place a square with side length t on the coordinate plane. So again, you're going to use the hint. So let's do this example. Place a square with side length t on plane, coordinate plane. So to do that, you're going to want to put one vertex at 0, 0. Yes?
So can the square be any size then?
Technically, but it's still it's still a square. And I don't put hash marks in because it's t long, so we just do t 0, 0, t, and then the last point would be at tt. So, yes, Rebecca.
What's the first one say?
Place a square with side length t on a plane, coordinate plane. So then, I'm going to do another one, another lots, because these are very helpful actually now that I look at them. I'm turning the page. In a minute. Okay, so this problem says given parallelogram RSTU with one side length K, labeled K, assign possible coordinates to the vertices. So we will write that down. Given parallelogram RSTU with one side length labeled K. Assign possible coordinates to the vertices. So if we're doing a parallelogram, you can put one at the origin, which is what I highly recommend on these. And then you could do, we could call that one R, and then we could do S, K units over from the origin. Because it's a parallelogram, we can draw these the same length. So this is going to be some random point X. We're going to call that A and B. So that's RS, this one will be T, this one's U. And then T, because it's a parallelogram, we have to move it over the same distance that this is from the y-axis. So this is going to come over A units. So it's K plus A, and then it's the same height. RS, so this is T, and it's K plus A, and then the same height, B. So this would be an example of putting a parallelogram with side length K, with one side length labeled K.
So the reason you didn't do K was because, like, instead of A and B was because it was a different height, or a different building, because it would only work in the square.
Yeah, rectangle.
Or,
So if you made this K high, that would be your B. Are you saying this would be 0? Like if you just went like 0K?
yeah.
That would be a rectangle. It can be that, like if A is 0 and B is the same height. This is more of a generic. So a lot of times, you'll notice on your proof papers that I'll put, you need to be more generic. So we don't use examples to prove something. We use variables. So here's a very generic parallelogram. You could actually get a rectangle or square out of this, just depending on what the points are.
Why did you have that K plus A?
Because this distance from the origin to here is K, and then I had to add that extra little bit, which is A, which goes to there.
Oh.
Okay, that's why. Okay. Okay, so another example, assign coordinates, and this is one where we wouldn't use the origin, to the vertices of an isosceles triangle with a height of 6 from the origin. Now, because we're not given how long the base is, again, we're going to want to use variables, not specific numbers. So if the height is 6 from the origin, we're just going to go straight up on the y-axis and put a dot. So this is 0, 6. Then in order to be isosceles, we have to be the exact same distance from each side of the origin. If these are congruent, then by the leg, right triangle congruence theorem, these two triangles will be congruent, and the sides by CPCTC would be congruent. So in other words, these have to be the same distances. But we don't have a specific number. We'll just say whatever x is, 0, and then we want to go negative x, that same amount to the left. And we'll just call this ABC. So here's an isosceles triangle, ABC, that has height of 6. I'm going to do one proof example on here. Basically, prove that the diagonals of a square are perpendicular. Okay? Prove that the diagonals, we're going to use a coordinate proof. Now, in order for lines to be perpendicular, what do you have to show? What can you show using using the lines themselves? Like, how do you know two lines are perpendicular? Excellent. That's what we want to focus on, okay? To one another. So we're going to place a square on the coordinate plane. Now we're not going to be specific. We're going to have 0, 0. We're going to have R 0. Because it's a square, this will be R, R, and this will be R, R. And this will be 0, R. And we will call this, we can call it whatever we want. So K, L, M, N. That way when we refer to segments, we have a name for them. So if we prove, we're trying to prove that these two are perpendicular, so we can find the slope between M and K. So slope, we use the letter M for slope. So we're doing the slope of M and K. We do the difference in the y, so R minus 0, and the difference in the x's in the denominator, R minus 0, which equals R divided by R, which is 1. if we can prove that the slope between L and N is -1, then we can say they're perpendicular. So the slope between L and N is 0 minus R divided by R minus 0. So it's -R divided by R, which is -1. And then we just write a concluding statement. Since the product of the slopes of segment MK and LN is, since the product of the slopes is -1, the diagonals are perpendicular. So that's the end of our video for this lesson.